Hello air cooling aficionados, I'm the Tech Wombat, and if you are thinking like me, then you want to have a quiet, yet powerful and maintenance-free workstation. So in this video I'm digging deep into the performance of BeQuiet's Darkrock Pro 4 CPU cooler in combination with Intel's Core i7-13700K CPU. I will measure the noise of the Darkrock Pro 4 and monitor the CPU's core clocks, package temperatures and throttling behavior at the default power limit of 253 watts. As workloads, I will be using some light multimedia and developer tasks, single and multi-core benchmarks, and gaming benchmarks. I will be testing everything on MSIs Z790 Tomahawk WiFi motherboard, together with 64GB of Kingston Fury Beast DDR5 5600 memory. As graphics cards, I use the Asus TUF Gaming RTX 4070 Ti. All is built into BeQuiet's Pure Base 500DX MIDI case, which itself comes with 3 PureWings 2 140mm case fans. I bought everything with my own money for my 2023 creator and developer PC build, so there is no sponsoring or other financial incentive involved. I bought the Darkrock Pro 4 at a discount from Amazon here in Germany. It came in a slightly damaged box. The Darkrock Pro 4 cooler is a aluminium dual tower dual fan 7 heat pipe CPU air cooler with a TDP of 250 watts. The cooler's length is 146mm, width is 136mm, height is 163mm, and it weighs 1130 grams. To get a grasp of the size of the cooler, watch this. It is paired with 2 of BeQuiet's own Silent Wings 3 PWM fans. The outer fan is the smaller one and has a diameter of 120mm. That way there is just enough space to access the memory. I guess it is the one with 1500 RPMs. The inner fan has a diameter of 135mm, and I guess it is the one with the 1200 RPMs. BeQuiet recommends to mount the cooler onto the mainboard outside of the case. It is so big though that I had trouble to install the motherboard with the cooler on it in the case and connect the CPU power cables with the case's default case fan location. After removing the top fan, I was able to install the motherboard and connect the CPU power. An adapter is included to connect both fans to the CPU fan header on the motherboard. As a result, only one fan speed will be reported, which is the smaller one. Therefore, I assume it is the one from the bigger fan. Let's have a quick look at the actual product specifications of Intel's Core i7-13700K. Here we see that its max turbo frequency is 5.4 GHz. To my understanding, this is only true for 1 or 2 cores during single-core workloads. When running multi-core workloads, the max turbo frequency of the performance cores is 5.3 GHz. The efficiency core's max turbo frequency is 4.2 GHz. The processor base power is 125 watts. The maximum turbo power is 253 watts. T-junction, which is the maximum temperature allowed at the processor die, is 100 degrees Celsius. Sometimes you read the term TJ-max, which I believe is this value. Next I will be doing some loudness measuring of the fan noise. As it is not possible to run load tests on the CPU without case fans, it is also not possible to measure the loudness of the CPU cooler alone during benchmarks. Therefore I decided to do it as follows. First, I measure outside of the operating system in the BIOS the loudness of the CPU cooler fans at different RPMs while the case fans are off. This will result in a table of RPM and dB. I call it the RPM to dB table. Next I will do the benchmarks and measure the loudness during each benchmark for the whole system, as well as the RPMs of all individual fans. With the RPM to dB table we will be able to determine how loud only the CPU cooler within the whole system is during every workload. Normally I'd put the PC under the table, but as many people seem to have it right next to them on the table, I created a similar setup. I put it on a small table to the right of my desk. I did the noise measuring on my iPhone 12 using the Decibel X app. I have read that this kind of loudness measuring is not as precise as a calibrated loudness meter, but it is only a couple dBs off, so it should at least give us a direction. As all values were measured in the same way, This at least should give you values which are correct relative to each other. During measuring, the case was closed and the distance between the iPhone's microphone and the case was 50 centimeters or close to 20 inch, to reflect kind of how far a person would be from the PC. I also make sure to position the iPhone with the microphone directed towards the PC. As you can imagine, this approach does not really conform to scientific standards, as I have no calibrated noise meter and no soundproof booth, but I tried to be as precise as possible given the circumstances. To give you a couple of reference values. Playing Fortnite with different loudness results in a noise between 38 and 66 decibels. A very quiet room, like for example a room with closed windows, has around 23.5 decibels. The limit of hearing is about 20 decibels. When a decibel value is 10 dB higher than another one, the higher one is perceived as around double the loudness of the lower one. Okay, now let's go into the BIOS. First, let's have a look into the hardware monitor console of my mainboard in the BIOS. Here we see in the top right corner the fan curve showing 13% PWM at 40 degrees Celsius, up to 100% at 85 degrees Celsius. The CPU1 fan is showing 0 RPM, but this is not really 0 RPM. It is only below 300 RPM, which seems not to generate a clear RPM signal for the mainboard. We also see the 3 case fans, system 1, 5 and 6, all of them showing around 550 RPM. Next I will deactivate the smart fan mode for the system fans 1, 5 and 6 and set it to 0 volt, in essence stopping the 3 case fans. Then I change the fan curve for the CPU cooler in a way that I can change the RPM in 10% steps. I measure the loudness and put it into a table. Then I increase the curve by 10% and measure the loudness again. You get the idea. That way we can see how loud the DarkRock Pro 4 is, separately, at a given RPM. This results in the following diagram and table, which I call the RPM 2dB table. Here we see, for example, that the DarkRock Pro 4 by itself created a fan noise of 33.7 dB when at 100% or 1250 RPM. Beyond 50% or 670 RPM, the noise was in the 24.6 to 24.9 dB range. At 80%, for example, the RPM was around 1000 and resulted in around 29 decibel of noise. Just one more reference point. Together with the case fans, this resulted in a total system noise of 38.3 dB when all fans were at 100% and 34.1 dB when all fans were at 80%. Let's also quickly look at my base configuration in the BIOS. The MSI Z790 Tomahawk factory settings are all unlimited. To my understanding, this means that there is no power limit, which results in the cooler option water cooler PL1 4096 watts. As on the cooler box it says that the TDP is 250 watts, I set the cooler tuning option to box cooler, which sets the PL1 to 253 watts. I ignore the difference of 3 watts for the moment. In part 2 of this video I will show how power limits relate to temperatures and vice versa. In the advanced CPU configuration menu, I left the long duration power limit and short duration power limit on auto, which defaults to the max value of the cooler, which we just set to 250 watts in the setup. I also disabled the enhanced turbo mode, as I have heard that this also leads to higher power consumption and as a result higher temperatures. During most of the non-game benchmarks, the graphics card's fans were stopped. Only one non-game benchmark actually used the GPU, but I will point it out later which one it was. As a general statement, I will do every desktop recording using OBS, recording 4K video in the background via NVENC codec on my NVIDIA RTX 4070 Ti. In my office workload I have 2 browser windows with text sites open. Then I started 2 4K 60fps YouTube videos which run in the background and a 1080p video in the foreground. Also, there is an instance of HWinfo running. I use it to monitor the core clocks of the individual cores, the CPU package temperature, if thermal throttling happens, the CPU package power, current PL1 and PL2 limits, if PL1 or PL2 limits were hit, the CPU fan speed, as well as the 3 system fan speeds. The CPU package temperature, CPU package power and CPU fan speed is shown each in a separate graph. The task manager is running as well for us to see how many cores are utilized. In that situation, we see that one P-core runs from time to time at 5.4 GHz. All other P-cores run at 5.3 GHz. All E-cores run at 4.2 GHz. The average package power is around 45 degrees Celsius at a room temperature of 20 degrees Celsius. We see the average package power at around 27 watts, the CPU fan beyond the threshold of reporting any RPS, the PL1 and PL2 limits are set to 253 watts, just as we saw in the BIOS. We also see that no thermal throttling takes place and neither PL1 nor PL2 power limits were hit. In the task manager, we see that only a handful of cores are moderately busy. The whole system produces a noise of around 28 decibels. The CPU fan run at below 350 RPM, which is, according to my RPM to dB table from before, around 24.6 decibel. Professionally, I am a business intelligence application developer for a global corporation. In my spare times, I sometimes do some coding. Therefore, let's look at a simple workload with Visual Studio Code. Here, I start a small mock server for a small web-based application, and then reload it with the Chrome DevTools in the background. This results in 2 P-cores running sporadically at 5.4 GHz. All other P-cores run at 5.3 GHz. All E-cores run at 4.2 GHz. The average CPU package temperature is around 47 degrees Celsius, again at room temperature of 20 degrees Celsius. Here we see the average package power at around 31 watts. The CPU fan again at very low voltages, which result in 350 RPX max, which is around 24.6 decibel for the CPU fans and 27.5 dB for the whole system. The CPU Z benchmark has a multi-thread part and a single-thread part. Both of them are very short. Nonetheless, the multi-thread part leads after only a couple of seconds to the CPU hitting the T-junction temperature of 100 degrees Celsius and starting throttling, despite the fact that the peak package power is around 235 watts. All P-cores are running at that time at 5.3 GHz. The CPU fan peaks out at 950 RPM, which according to the RPM to dB table is around 28 decibels. The whole system peaked out at 35 decibels. The multi-threaded score is 12,389 and the single thread score is 845. In the 7-zip benchmark, all P-cores run at 5.3 GHz. E-cores at 4.2 GHz. The CPU package temperature did not hit the T-junction and maxed out at 96 degrees Celsius, with a room temperature of 20 degrees Celsius. There was no thermal throttling. The CPU package power maxed out at around 230 watts, with an average of 176 watts. As the temperature reached 85 degrees Celsius, all fans run at max RPM, which means that the CPU fan reached around 33.7 dB and the system as a whole 38.4 decibels. The benchmark score was 158.2 GIPS. Next up, let's look at some serious workloads with Cinebench R23. If you don't know Cinebench, it is a pure CPU benchmark which can run on one or all cores of a CPU. It then does a countdown of 10 minutes in which it renders the same scene of a living room over and over again. So let's first look at a single core performance. In the task manager we see that 2 threads are active. We see all P-cores running at 5.3 GHz, E-cores at 4.2 GHz. The CPU package temperature peaks at 70 degrees Celsius and averages out at 58 degrees Celsius at a room temperature of 20 degrees Celsius. There was no thermal throttling. CPU package power maxed out at around 57 watts with an average of 38 watts. As the temperature did not reach 85 degrees Celsius, the fans also did not run at max RPM. This resulted in CPU fan RPM around 550, which is according to the RPM to dB table near 24.8 decibels. The system as a whole produced 32 decibels. This bench run resulted in 1981 points. In the multi-core benchmark in Cinebench R23, the situation looks quite different. In the task manager we see that all 24 threads are active. The CPU package temperature reaches T-junction temperature of 100 degrees after less than 2 seconds, as always at a room temperature of 20 degrees Celsius. The CPU starts thermal throttling immediately, which reduces the P-cores clocks to around 5.2 GHz and the E-cores clocks to 4.1 GHz. During the same time, the CPU package power reaches 269 watts, and therefore the CPU limits the package power to PL2, which we set to 253 watts. After around 20 seconds, all fans run at 100%, meaning the CPU fans run at around 1260 RPM and the case fans run slightly over 1000 RPM. This results in 33.7 dB for the CPU fan, according to the previously established RPM to dB table, and 38.2 dB for the whole system. Normally, after 50 to 100 seconds, the CPU will switch to PL1 power limits, but as PL1 limit is the same as PL2, which both are 253 watts, the only thing the CPU really can do to keep temperatures at 100 degrees Celsius is lowering the CPU clocks further. The P-cores go down to 5.1 GHz and E-cores to 4 GHz. This leads to lower package power between 200 and 240 watts. This results in 28,873 points. Now let's look at the Blender benchmark 3.4.0. It renders 3 scenes either by utilizing the CPU or the GPU. Let's run it working on the CPU first. Similar to the Cinebench multi-core benchmark at a room temperature of 20 degrees Celsius, it reaches the T-junction temperature of 100 degrees Celsius after 4 seconds and starts thermal throttling then by reducing the P-cores to 5.2 and the E-cores to 4.1 GHz. After around 20 seconds, all fans run at 100%, resulting in a total system noise of 38.3 decibels and a CPU fan noise of 33.7 dB, according to the aforementioned RPM to dB table. Interestingly, it takes until the third benchmarking scene to hit the PL2 power limit. This benchmark results in 413.64 points. Now comes the interesting part. When running the benchmark using the GPU, the load on the CPU and therefore on the cooling solution, as well as the final score, is quite different. I will run it on my Asus TUF Gaming GeForce RTX 4070 Ti. We see in the task manager only short spikes on all cores. We also see that no thermal throttling takes place. The P-cores clock at 5.3 GHz and the E-cores at 4.2 GHz. We see an average CPU temperature of 54 degrees Celsius and an average package power of around 40 watts. The average CPU fan speed is 450 RPMs, which means around 24.7 dB. The total system noise is 31.2 dB. This benchmark run results in 6811.55 points, which is more than 16 times higher than on the CPU. You will see the fact that high compute workloads can mostly be offloaded to the GPU in games as well. Now let's look at a game using the Unreal Engine 5, which is Fortnite. Fortnite does not have a proper benchmark, but we primarily are interested in temperature, power and CPU fan speed, so I thought this is probably fine. This runs on my Asus TUF Gaming GeForce RTX 4070 Ti. This benchmark runs at low quality settings and with 720p without DLSS, TSR or ray tracing. The reason for that is to have the CPU as the limiting factor instead of being limited by the GPU. We can observe this by looking at the first number in the first line, which shows the GPU utilization in percent. It never reaches 100% in 720p. That way we can also identify the highest load on the CPU possible by the game at hand, and therefore the highest possible CPU package power, the CPU temperature and CPU fan speed, and therefore the CPU fan noise. We see all P-cores at 5.3 GHz and E-cores at 4.2 GHz, which means there is no thermal throttling, which you also see in line 11. We see mostly only a few cores utilized. The CPU package temperature is 70 degrees Celsius. The CPU package power is between 125 and 150 watts. CPU fans run around 850 to 1000 RPM, which means between 26 and 29 decibels. The whole system runs at 36 decibels. The average FPS is around 300. Just for your reference and comparison, the loudness of the game sounds from my speakers is between 38 and 66 decibels. When running Fortnite in 4K with DLSS on and ray tracing off, we can see that now the GPU is the limiting factor. We see the GPU utilization in the first line and it shows 98 to 99%. We see the CPU package temperature between 56 and 80 degrees C and the package power between 58 and 103 watts, and therefore no thermal throttling. The CPU fan RPMs are between 600 and 850, which means a fan noise between 24.8 and 27.2 decibels. I recorded the whole system noise at 34.3 decibels. The average FPS was 56. Next up is Red Dead Redemption 2 in 720p with low quality settings without DLSS, TSR or ray tracing. Here we see a similar picture like in Fortnite. We see only a handful of CPU cores utilized. As a result, the CPU temperature is around 70 degrees C. The CPU package power moves between 115 and 139 watts. No thermal throttling takes place. The CPU fan runs at around 850 RPM, resulting in noise of around 26 to 27 dB. The system as a whole created a total noise of 35.1 dB. The average FPS at the end of the benchmark is close to 188 FPS. In 4K with DLSS on and ultra quality, despite the fact that low quality textures seem to have been used, we see again only a handful cores utilized. The average CPU package power in the shooting scene is 105 watts. Average CPU package temperature is 72 degrees Celsius. No thermal throttling. Average CPU fan RPM is 900, resulting in a fan noise of around 27.2 dB. The total system noise is 36.4 dB. Average FPS in 4K is close to 105. The third and last game here is Watch Dogs Legion, as it uses some ray tracing effects. In the 720p benchmark run I use again low settings with no DLSS and ray tracing to push the CPU as hard as possible. During the run only a handful of cores are utilized. The average CPU package temperature is 68 degrees C. The average CPU package power is 110 watts, with the average CPU fan speed of 800 RPM, resulting in 25.5 dB from the CPU fan and 34.3 dB from the whole system. No thermal throttling takes place. The benchmark finishes with an average of 155 FPS. In 4K I use a mix of high and ultra settings with ray tracing on and DLSS quality. We again see only a handful of cores utilized. The average CPU temperature is 62 degrees C. The average CPU package power is 90 watts. Average CPU fan speed of 700 RPM, which is around 25 decibels, and a total system loudness of 34.6 decibels. Again, no thermal throttling. In the end, we see an average of 54 FPS. We saw that in almost all benchmarks, the system noise was far higher than the CPU fan noise itself. This is not only due to the fact that the PureWings 2 140mm fans, which come with the PureBase 500DX case, are generally louder than I like it. It is as well due to the fact that 4 fans together are louder than each of them separately. Nonetheless, after most of the parts of this video were recorded, I decided to replace the PureWings 2 140mm case fans with 3 of BeQuiet's Silent Wings 4 140mm PWM high-speed fans. At comparable RPMs, they are generally quieter, but they are low for higher RPMs. On the other hand, at higher RPMs, they are louder as well. At idle and office work, the PC is now close to inaudible. In numbers, in all workloads, the system noise is 2 to 3 decibels quieter with the Silent Wings 4 fans when compared to the factory build with the PureWings 2 fans. The performance is mostly the same, although I set the fan curves in a way that they only go up to around 1250 RPM, rather than the max RPM, which is 1900. Only in the most demanding workloads, the performance seems to be 2 to 3% lower, but I was not able to get a clear number even though I did at least 10 benchmark runs. In this video we saw that the Darkrock Pro 4 handles most of the workloads very well. Everyday office and development workloads and games using a handful of cores will be handled competently, with average CPU package temperatures between 40 and 80 degrees Celsius, assuming a room temperature of 20 degrees Celsius, and moderate CPU package powers between 25 and 150 watts. Only when it comes to sustained multi-core workloads, like the Cinebench R23 multi-core or the Blender benchmark using CPU, this leads to temperatures at the T-junction limit of 100 degrees Celsius, combined with thermal throttling and utilizing power limits. The reported CPU fan RPMs are between 300 and 1250, which translates to 24.6 and 33.7 decibels, which I find to be quite enough for a CPU cooler made by a company literally called BeQuiet. As said before, replacing the PuWings 2 with the SilentWings 4 fans lowered the total system noise at every workload by 2 to 3 decibels, with fan speed kept to 1250 RPMs, and at idle it made the PC even inaudible. If you are aiming for sustained highest load multi-core workloads, then you probably are targeting high performance rather than low noise. In that case, the Darkrock Pro 4 is probably not the best option, as the CPU throttling reduces the CPU frequencies around 200 to 300 MHz over time. There seems to be other CPU air coolers which allow for higher performance, but they are notably louder as well. For people looking for a reasonable quiet PC who only render a video from time to time or compile the Chromium browser occasionally, this is probably an acceptable trade-off. This raises the question what one can achieve in terms of lower temperatures with the Darkrock Pro 4 in combination with Intel's Core i7-13700K. I decided to create part 2 video where I will go deeper into tweaking the CPU's PL1 and PL2 power limits and temperature limits as well, to try to find out the optimal combination of power limits, loudness, and CPU package temperatures. Check it out if you are interested in such things. If you liked this video, please help me out by liking and subscribing. If you didn't like it, thumbs down or write me in the comments. I am the Tech Wombat. Thank you for watching, take care and goodbye.